So we said that chemical reactions, they are divided into two types, redox and non-redox. And with redox, you can have decomposition similar to non-redox, single replacement for redox, double replacement for non-redox, and then combination for both redox and non-redox. So combination and decomposition reactions, they exist in both redox and non-redox reactions. With non-redox, you have double replacement, and with redox, you have single replacement. We're going to define all of these types of reactions, but these are the reactions mainly in chemistry. So let's start with the first one, which is the decomposition reaction. This reaction can be either redox or non-redox. What is it? It's actually, you start with one substance. So you start with A in there, it's one substance, and that substance, you break it down. So this is why it's called a decomposition reaction, because you're breaking it down into two or more simpler substances. Um, Example. So example in here, I'm starting with hydrogen iodide, and I am breaking it into hydrogen and iodine gas. And let's have an example, or let's see what type of reaction is this, because decomposition reactions, they can either be redox or non-redox. So let's see if there is a redox or non-redox in here. To be a redox or non-redox, you need to have a reduction and oxidation reactions within the reaction. So let's see. Um, for the hydrogen, remember what we said. You have to look at every element in the reactants and see, did it gain or lose in the product. And this is how you decide if you're doing a reduction or an oxidation reaction. So hydrogen over here is +1, right? And the iodine is -1. Hydrogen became 0, and nitrogen is 0. Okay, so these are gases. These are diatom gases. So the oxidation number for those is 0. These are uncombined elements. So what am I doing here? If you take a look, you would see that hydrogen went from +1 to a 0, right? So hydrogen gained electrons. So from plus means losing. I'm going from plus to 0. Then this means that hydrogen is gaining. Gaining means reduction. So this is going to be my reduction. So we say that this is a reduction half reaction. And then iodine, on the other hand, went from 1, -1, it went to 0. So iodine was -1, it was already gaining, and it went to a 0, so it lost, right? So losing means oxidation. If I have a chemical reaction where A turns into B plus C, and within the reaction, I have two half reactions, reduction and oxidation, then I'm going to call this a redox, decomposition reaction. Okay, so this reaction is a decomposition reaction, and because I have oxidation and reduction half reactions within it, then it is going to be a redox decomposition reaction. This is another example of decomposition where A turns into B plus C, right? So, by the way, make sure when you do the reduction and the oxidation half reactions, make sure that the equation is balanced before doing this, okay? So here the equation is balanced. I'm just going to proceed forward. Calculate the oxidation number for every single element. So hydrogen here is going to be +1. Remember, the carbonate, the CO3, this is how I do it. The CO3 in there is 2 negative, right? So if the CO3 is 2 negative in there, I don't know what's the oxidation state of carbon, but I know that oxygen is -2, and I have 3 of the oxygens. This whole thing is going to be -2. So x minus 6 is equal to -2. X is equal -2 plus 6, so x is equal to +4. So now I know that the carbon is going to be +4 in there, right? And the oxygen is going to be -2. Going to carbon dioxide in here, Oxygen is still -2. So -2 times 2, this is -4. So this carbon has to be +4 to balance that. And the hydrogen here is a +1. So I have a +2 for the hydrogen. So I need a -2 to balance for the oxygen. So the oxygen here is a -2. Notice what I have here, you guys. I'm not changing the oxidation state because the oxidation state for the carbon was +4. It remained a +4. And the oxidation state for the oxygen was -2. It remained -2. And the oxidation state for the hydrogen was +1. It remained a +1. So nothing is changing in here. So I would say this reaction is an example of a non-redox, but it is a decomposition reaction. So see the difference in there between a non-redox and the redox reaction? Both are decomposition. A gives you B plus C. Okay, so this is another example of a redox reaction. So this is a redox. It's a decomposition reaction. A gives you B plus C. It's another example. Do your oxidation state. You have an oxidation. You do have a reduction in there between the oxygen and the hydrogen. So this is a redox decomposition reaction. This is another example in there where water decomposes into hydrogen and oxygen. So you're going from +1 to 0 and then -2 to 0. -2 to 0, you are losing. But +1 to 0, you are gaining. The 0 is your basically your standard in this case. So going from 0 to +1, because 0 you're gaining, right? So going from 0 to +1, this means that you are going to lose. And going from 0 to -2, this or -1, let's keep it -1. This is going to be gaining in this case. So you're going to gain if you go from 0 to -1 because negative means gaining, positive means losing. On the other hand, if you're going from +1 to 0, then you are going to gain. Okay, and if you go from -1 to 0, then you are going to lose. Okay. The other type of reaction is called a combination reaction. Combination, as the name says, I am having in my reactants two components that I'm going to combine them together, and in the product, I'm just going to form one product in there. So two or more substances react to form a single product or a single substance, and this is called a combination reaction. Combination reaction may be either a redox or a non-redox reaction. So we're going to do exactly the same as we did earlier in there. Let's have an example. So two reactants combine together to get one product. This is a combination reaction. To find if it's a redox or a non-redox, calculate the oxidation number of each. So sulfur is a non-combined element. Oxygen is a non-combined element in this case. Sulfur here is going to be -4 because it needs to balance the oxygen, which is -4 as well. So sulfur is -4. I can see the change in the oxidation numbers, you guys. Sulfur is going from a 0 to a negative, so sulfur is gaining. Positive. It has to be positive in here. So it is going from 0 to +4, so it is losing. So this is going to be oxidation. And oxygen is going from 0 to -2, then this is going to be gaining. So this is going to be a reduction. So if I ask you what is our reducing agent, our reducing agent here is going to be the sulfur, and the oxidizing agent is going to be the oxygen. This is an example of a redox combination reaction. This is a redox combination reaction. Okay. Dinitrogen pentoxide. These are two nonmetals. You're reacting those with water. You're forming nitric acid. So calculate the oxidation state for the nitrogen. Here, go ahead and put it in an equation. You can put it in an equation. You don't know the oxidation state for nitrogen, so I would do 2x. I know that oxygen is -2, so I would do +5 minus 2, and that is equal to 0. So 2x minus 10 is equal to 0, and x here is going to be +5. So now I know that the oxidation state of the nitrogen is going to be +5. The oxidation state of the oxygen, I know it is -2. And then the hydrogen here is going to be +1. The oxygen is going to be -2. Same thing, we can do the same thing, put it in an equation, calculate the nitrogen in the product, and the nitrogen will be +5 oxidation state. And the oxygen is going to be -2 in there. Nothing is changing. So the nitrogen remains a +5, the oxygen remains -2, and the hydrogen remains +1. So this is going to be an example of a non-redox combination reaction. Let's have another example here. Hydrogen, fluorine, you're forming HF, right? So hydrogen is a 0, fluorine is a 0. I'm changing now the oxidation number for the H and for the fluorine. This is the oxidation state. So going from a 0 hydrogen to +1 hydrogen, you choose the same element. See what happened to them. So that is oxidation because hydrogen lost an electron. And from 0 to -1, fluorine gained an electron. So this is going to be the reduction half reaction. So this is an example of a redox combination reaction. Okay. Another example for the aluminum, bromine in there. These are simple. So aluminum solid, bromine. This bromine here is a liquid. Okay. You guys, I missed a bromine is always a diatom, so it's going to be a Br2. So please write it as a Br2. I'm going to form aluminum bromide. The aluminum is a +3 because it's a group number 3, and the bromine is -1, so that is going to be -1 in there. And either -1 or if you want it to be -3, but I'm just looking at just the bromine in there. Each Br is -1. So I would say, okay, I'm going from aluminum 0 to aluminum +3. Aluminum is losing. So that is going to be oxidation. And then I am going from bromine 0 to bromine -1. Bromine is gaining, so that is going to be my reduction. And this is an example of a redox combination reaction. Okay. The third type is a single replacement reaction. So a single replacement reaction is always a redox reaction. And it occurs when one element reacts with a compound, displaces one of the elements from the compound, and becomes part of a new compound. So you do A plus BX. So over here, B is being displaced. So B now becomes an element, B, and then you will have an AX. This is called a replacement. It's a single replacement, okay, plus an AX. So A and B now are going to be elements, and A and X are going to be compounds. Something like this, okay? So you're starting with an A. This is BX. So B will become now an element, and then the zinc and the sulfate will combine with each other. This is always a redox reaction. So you can easily do the oxidation numbers for each one of those and see that zinc turned into a +2, copper turned into a 0. So copper gained and zinc lost. Zinc lost means it's oxidation. So if it's zinc, we say that zinc is being oxidized. So this is the term that we use. So we say that zinc is oxidized, and we say that zinc is the reducing agent. Okay, and then here we say that copper is being reduced, and the whole thing, the copper sulfate, the whole thing is the oxidizing agent. Okay, So when we look at the oxidizing and the reducing agent, it's the reactants, whatever is in the reactants in there. One of them is going to be the reducing agent, the other is going to be the oxidizing reagent whenever we are working with a redox reaction. So this one is a single replacement redox reaction. Let's have another example in here where we are doing hydrogen. Hydrogen is a 0. Copper oxide. So oxygen is -2, right? So copper needs to be +2 in there. And then we're going 0. And then hydrogen is going to be +1. Oxygen is going to be -2. So I am going from hydrogen 0 to +1. See? Then this is going to be my oxidation half reaction. And I'm going from copper +2 to a 0, and that is going to be my reduction. It is gaining. It is gaining. It was plus, and then it became a 0, so this one is going to be my reduction half reaction. It is a single replacement in there. Copper is going to be now my solid. This is going to be my element that is formed, and then the hydrogen will combine with the oxygen. Another example, copper solid, silver nitrite, forming an Ag+. So this is going to be my single replacement in there. This is a 0. Silver is going to be +1 because the nitrate. The whole thing is -1. Okay. The whole thing is -1. You don't have to calculate the oxidation state of the nitrogen and the oxygen. Why? Because here it's obvious. I'm looking at what happened to the copper and the silver. So if you can find one element that is being oxidized and the other element is being reduced, just go for it. You don't even have to calculate the oxidation state for every single one of them. So here I can say that copper is going from 0 to +2, right? So if it's going from 0 to +2, then this is going to be my oxidation half reaction. And then silver is going from +1 to 0. This is going to be my reduction half reaction. As long as you can find like an element or an element in there in the reactants that is losing, another one that is gaining, then you're fine. Okay, so that is going to be a redox combination. It's a single replacement, not combination, single replacement reaction. Now for the double replacement, it's double, right? So if it is double and both of them are going to undergo a reaction and you're going to have a replacement there. So A will replace B and B will replace A. So you're going to get BX and AY. This is a double replacement reaction. This reaction is never a redox reaction. It's never a redox reaction. It's a simple non-redox double replacement reaction. So it's a non-redox double replacement reaction. Okay, so here I'm starting with barium nitrate. I'm reacting it with sodium sulfide. I get a barium sulfide and sodium nitrate. So you can easily see that I am replacing both substances in there. So that is going to be a double replacement reaction. Same thing there. NaOH, HF. I mean, you can double check. The sodium is going to be +1 here. It stayed a +1 in there. The fluorine is -1. It stayed -1 in there. Same charge for the oxygen and the hydrogen. The hydrogen is +1. Oxygen is -2. It remains the same. Nothing is changing. So this is an example of a double replacement reaction. Let's have more examples in here. So classify the following. Sodium hydroxide, HCl. This one is a double replacement reaction. So this one is considered to be a non-redox reaction. It is a double replacement. Magnesium and oxygen, this is a 0, this is a 0, and then this is +2, this is -2. You can see that you're having oxidation and you are having reduction in this case. So this one is going to be a redox reaction, and it is a combination reaction. You're combining A plus B and you're getting C. Okay, this one is a decomposition. You're starting with A and it's becoming B plus C. We're going to figure out if it's redox or non-redox do the charges. So sodium is going to be +1. It remained a +1. Carbon is going to be +4. It remained a +4 in there because oxygen is -2. So nothing is changing. So this one is going to be a non-redox reaction, and it is a decomposition reaction. And the last one is a single replacement reaction, and magnesium is 0, that is +2. So you can see that I am doing oxidation in this case. And then for the chlorine, this is -1, and the chlorine became, I can see here this -1. So nothing happened to the chlorine, but the hydrogen is +1, it became 0. So +1 and 0, this is going to be my reduction. This one is going to be my oxidation. As long as you can find an element in there that is losing or gaining electrons, then this is going to be a redox reaction, and it is a single replacement.